Since the beginning of history, humans have tried to explain the origins of the universe. From ancient myths to religious beliefs, people have sought to understand how everything came to be. However, in the modern era, science has provided a compelling answer to this age-old question, the Big Bang Theory. This theory explains that the universe began as a singularity, rapidly expanded, and has been expanding ever since. The universe is vast, filled with galaxies, stars, and planets. But how did it all begin? Scientists believe the universe originated from a single point in an event known as the Big Bang. This theory explains how the universe rapidly expanded from an incredibly hot and dense state to the cosmos we see today. But what exactly happened during this event, and how do we know it took place? To answer that, we must first review how this theory was created. The Big Bang Theory has been shaped by groundbreaking discoveries for centuries. In the past, people believed the universe was static and unchanging, with celestial objects fixed into place. However, in the early 20th century, Albert Einstein's theory of general relativity hinted that space itself could be dynamic. His equations suggested that the universe should either be expanding or contracting. Initially, Einstein introduced a cosmological constant to maintain a static universe, but later called it his greatest mistake. One of the first scientists to propose the idea of an expanding universe was the Belgian priest and physicist Georges Lemaitre. In 1927, he theorized that the universe has originated from a primeval atom, a single point that expanded to form everything we see today. His work laid the foundation for what would be known as the Big Bang Theory. The real breakthrough came in the 1920s when an astronomer named Edwin Hubble made a remarkable discovery. By observing distant galaxies, Hubble noticed that their light was shifted towards the red end of the spectrum, a phenomenon known as redshift. This redshift indicated that the galaxies were moving away from us, implying that the universe was expanding. This realization led to the idea that if we rewind time, all matter and energy must have originated from a single dense point, a concept that became the foundation of the Big Bang Theory. The process of the Big Bang can be broken down into key stages, each describing how the universe evolved from its earliest moments. The first stage is a singularity. Approximately 13.8 billion years ago, the entire universe was compressed into an unimaginably small, hot, and dense state. This singularity contained all matter, energy, and space that would eventually form the cosmos. The laws of physics as we know them break down at this point, making it difficult for scientists to fully understand what existed before this event. Next came the rapid inflation. In a fraction of a second, within the first 10 to the negative 36th power to 10 to the negative 32nd power seconds, the universe expanded exponentially, going from smaller than an atom to billions of times its original size. This stage, known as cosmic inflation, set the foundation for the large-scale structure of the universe we see today. It also helped explain why the universe appears uniform in all directions, as inflation smoothed out any irregularities in the early cosmic fabric. As inflation slowed, the universe entered the quark-gluon plasma phase. The temperature remained extremely high, preventing atoms from forming. Instead, the fundamental particles such as quarks and gluons roamed freely. These particles will later become the building blocks of matter. As the universe continued to cool, quarks combined to form protons and neutrons through a process called hadronization. After about 3 minutes, the process of nucleosynthesis began. Protons and neutrons fused to create the first simple elements, mainly hydrogen and helium, with trace amounts of lithium. This stage determined the elemental composition of the early universe, which remains consistent with observations made today. When observing the universe, majority of the elements present are these basic light elements, showing strong evidence for the Big Bang Theory. Around 380,000 years after the Big Bang, the universe has cooled to approximately 3000 Kelvin, allowing electrons to combine with atomic nuclei to form neutral atoms. This period, known as the recombination, was a critical milestone because it made the universe transparent to light. Before recombination, photons were constantly scattered by free electrons, preventing light from traveling freely. Once neutral atoms are formed, light can move unimpeded, creating the cosmic microwave background. The cosmic microwave background is a crucial piece of evidence supporting the Big Bang Theory, as it is a faint glow of radiation that serves as a snapshot of the early universe. This radiation, discovered in 1965 by Arno Penzias and Robert Wilson, is remarkably uniform, providing insights into the conditions of the universe when it just began. With the universe now transparent to light, the next major phase was the formation of the first stars and galaxies. Gravity pulled gas clouds together, igniting nuclear fusion and giving birth to the first stars. These stars, known as the population 3 stars, were massive and short-lived, burning through their fuel quickly before exploding in supernova. These explosions brought heavier elements to the universe, which later contributed to the formation of more complex celestial bodies. Over time, these stars grouped into galaxies, setting the stage for the cosmic structures we can see today. But how do we know all of this happened? Scientists have gathered strong evidence supporting the Big Bang Theory. The first evidence is the cosmic microwave background, which serves as the afterglow of the Big Bang, providing a glimpse into the universe's infancy. The cosmic microwave background varies slightly in temperature, known as anisotropies. These correspond to regions of different densities in the early universe. Regions that were slightly denser in the early universe would have a more gravity, pulling in more matter and eventually forming galaxies and galaxy clusters we can see today. Another piece of evidence is the redshift of galaxies. Just like the Doppler effect, when a siren sound stretches as it moves away, light from distant galaxies is shifted towards the red end of the spectrum. This indicates that galaxies are moving away from us, confirming that the universe is still expanding, just as the Big Bang predicts. The discovery and acceleration expansion, driven by the dark energy, further supports the idea that the universe has been evolving since its initial explosive birth. Additionally, the abundance of hydrogen and helium in the universe aligns perfectly with theoretical predictions from the Big Bang nucleosynthesis. If the universe had no beginning, we would expect a different ratio of elements than what we observe. We observe our universe to be about 75% hydrogen and 25% helium, which matches the predicted ratios from the Big Bang. Despite the overwhelming evidence and research into this theory, many mysteries still remain. Scientists continue to explore what may have caused the Big Bang, what existed before it, and whether the universe will expand forever or eventually contract. With some theories such as the multiverse hypothesis suggests that our universe is just one of many, each with its own unique properties. Others explore the possibility of a cyclic universe, where expansions and contractions occur repeatedly over a cosmic time scales. The universe has a beginning, but what about its end? Scientists have proposed three main possibilities for how the universe might meet its fate: the Big Freeze, the Big Crunch, and the Big Rip. The first most widely accepted scenario is the Big Freeze, also known as the heat death of the universe. In this scenario, the universe continues to expand indefinitely. As it stretches, galaxies drift further apart, stars burn out, and new ones fail to form. Over trillions of years, the universe becomes cold, dark, and lifeless, with all of its energy evenly spread out, making any form of life or activity impossible. The second possibility is the Big Crunch. If the gravitational pull of all matter in the universe is strong enough, it could eventually slow the expansion and reverse it. The universe would begin to contract, galaxies would collide, and everything would collapse into a hot, dense state, similar to how it all began with the Big Bang. Some theories suggest that this could lead to a cycle of endless expansion and contraction. The third and most dramatic scenario is the Big Rip. This would occur if dark energy, the mysterious force accelerating the universe's expansion, grows stronger over time. Eventually, this expansion would tear galaxies, stars, and even atoms apart. In the final moments, even the fundamental forces holding matter together would fail, leaving nothing but a void behind.